Now let us do this problem here. In an isothermal expansion of 1 mole of oxygen with a temperature of 300 Kelvin, the gas absorbed an amount of heat Q is equal to 2 kilojoules. By what factor did the volume occupied by the gas increase? Right? So this is an isothermal expansion, okay, and 1 mole of oxygen gases there in the is at temperature of 300 Kelvin, okay, and the gas absorbed an amount of heat which is equal to 2 kilojoules. So by what factor did the volume occupied by the gas, okay, increase? How much the volume increases, or what is the ratio of final volume to initial volume? So now let us take here the case of ideal gas. Ideal gas. So I'm going to take an ideal gas now. Okay. So if I take an ideal gas here, so this is an ideal gas I'm going to take. So in an ideal gas, you know that the work done by isothermal process, and here this is an n is equal to 1. The number of moles is how much? 1 mole of gas. Okay, so the work done by the isothermal process is given by what? Work done by isothermal process is given by RT into natural logarithm of V2 divided by V1. RT into natural logarithm of V2 divided by V1. This is the, and also from this is the work done by isothermal process. This is the work done by isothermal process. Now from the first law of thermodynamics, we get the amount of heat absorbed, let me call Q, is equal to the change in internal energy plus the work done, right? And here this is an isothermal process. It's an isothermal process. Okay, and in isothermal process, you know that the temperature is equal to constant, and if temperature is constant, then the change in internal energy is equal to 0. Change in internal energy is 0, which means the heat absorbed is equal to the work done, right? So heat absorbed is equal to the work done. So I have already got the work done formula. Work done formula is this. This is the work done formula, RT into ln of V2 by V1. And this work done is equal to the heat absorbed. Okay. So that means I can write heat absorbed Q is equal to RT into natural logarithm of V2 divided by V1. Okay, so I can write here RT into natural logarithm of V2 divided by V1. This is the heat absorbed. So you can write this as Q divided by RT is equal to natural logarithm can be written as log to the base E V2 divided by V1. So which means V2 divided by V1 can be written as E to the power Q divided by RT. Okay, and what is the value of Q given to you? Q is given to you as 2 kilojoules. Q is given to you as 2 kilojoules. What is R? R is equal to 8.314 joules per mole Kelvin. Okay, this is the universal gas constant, and the temperature. So what is the temperature given to you? Temperature is given as 300 Kelvin. So temperature is equal to 300 Kelvin. So if you substitute these values, you will get V2 divided by V1 is approximately equal to 2.23. This is what you will get, the value of V2 divided by V1. That means the volume has increased how many times? 2.23 times. So this is a case when we are taking an ideal gas, right? Now let us take a real gas. For real gas, okay, So if I'm taking a real gas, you know that from the fundamental equation for thermodynamics. What is the fundamental equation of thermodynamics? We have the fundamental equation of thermodynamics. Fundamental equation of thermodynamics. What is it? It says that the internal energy change du is equal to T ds minus P dV, right? Where what is du? Du is the change in internal energy. Change in internal energy. And what is the change in internal energy? T is the absolute temperature. T is the absolute temperature. Okay, ds is the change in entropy. Change in entropy. Okay, and P is the pressure, and dV is the change in volume. Okay, so this is the first law, fundamental equation for thermodynamics. Du is equal to T ds minus P dV. Okay, so using this equation I'm going to solve. So we are going to find out what is the volume change here for a real gas. Okay, in the same question which we have seen before. So we will see what is the change in the volume, how much time the volume increases in a real gas. Okay, so for that we have this ds. You know that S is a function of volume and temperature. The entropy is a function of volume and temperature. So I can write ds, I can write it as dou S by dou T, dou S by dou T at constant volume into dt, okay, dt plus dou S divided by dou V at constant temperature into dV. So you can write this ds as like this. Okay, let me call this as equation number 1. So ds is equal to dou S by dou T at constant volume into dt plus dou S by dou V at constant volume into dV. Alright, now from Euler's reciprocity, Euler's reciprocity, you can write Euler's reciprocity. Okay, before that using the Euler's reciprocity, we have the we are going to use, I'm going to take a Helmholtz equation, right? So Helmholtz equation, what is Helmholtz equation? Helmholtz equation, Helmholtz equation, right? So Helmholtz equation says that dA, the Helmholtz energy, okay, that is equal to minus S into dt, minus S into dt minus P into dV, right? So Helmholtz energy is given by minus S into dt minus P into dV. So here you can see that if you differentiate dou A by, sorry, dou by dou V, dou by dou V of dou A by dou T. So dou A by dou T. Okay, dou A by dou T if you take at constant volume, dou A by dou T if you take at constant volume, dou A by dou T if you are taking at constant volume, okay, that should be equal to dou by dou T of dou A by dou V, dou by dou T of dou A by dou V at constant temperature. So so you can see here that dou by dou V, okay, this is the Euler's reciprocity. This is Euler's reciprocity. Euler's reciprocity. So Euler's reciprocity says that here you can see here A, V and T. We are connecting A, V and T, right? So I can write dou by dou V of dou A by dou T at constant volume is equal to dou by dou T of dou A by dou V at constant temperature. This is called Euler's reciprocity. Alright. Now here you have, so once again I will write here dou by dou V of dou A by dou T. Okay, dou by dou V of dou A by dou T at constant volume is equal to dou by dou T of dou A by dou V at constant temperature. Now you have the equation dA is equal to minus S into dt minus P into dV. This is your Helmholtz equation, minus P into dV. Okay, so you can see here that dou A by dou T, if you see dou A by dou T, dou A by dou T, okay, dou A by dou T at constant volume. If you see constant volume, here I have taken constant volume, dou A by dou T is minus S. And what is dou A by dou V? Dou A by dou V at constant temperature, dou A by dou V at constant temperature, here you can see dou A by dou V at constant temperature is nothing but minus P, right? So if if I substitute here, so what do I get? You will get dou by dou V of dou A by dou T, that is minus dou S by dou V at constant temperature. Okay, minus dou S by dou V is equal to what you will get, minus dou P by dou T. So dou S by dou V is at constant temperature, isn't it? Dou S by dou V is at constant temperature. So you can write dou S by dou V at constant temperature is equal to dou S by dou V at constant temperature is equal to what? Dou P by dou T at constant volume, right? So dou P by dou T at constant volume. So dou S by dou V at constant temperature, dou S by dou V at constant temperature is equal to dou P by dou T at constant volume. So let me call this equation, I am getting here an equation, so let me call this as equation number 2. Okay, so we have just used the Euler's reciprocity and applied the Helmholtz equation here. Okay, and then we got this relation, that is dou S by dou V at constant temperature is equal to dou P by dou T at a constant volume, right? Now from the second law of thermodynamics, you have the equation, that is TdS is equal to du plus PdV. This is second law of thermodynamics. TdS is equal to du plus PdV, isn't it? TdS is equal to du plus PdV. Now in this, if you take T into you know that du is equal to Cv into dt, right? Du is equal to Cv into dt. So you can also write this as Cv into dt plus PdV. Cv into dt plus PdV. So if you find du T into dou S by dou T, okay, T into dou S by dou T. What is T into dou S by dou T? Dou S by dou T at constant volume tau into dou s by dou t at constant volume will be equal to Cv, isn't it? T into dou s by dou t at constant volume will be equal to Cv. Let this be equation number 3. So I'm taking this equation here, second law of thermodynamics. I'm taking the second law of thermodynamics, and tau into dou s by dou t at constant volume, I'm finding constant volume, you will get Cv. Right now, so you can rewrite this equation, the equation 1. You have the equation 1 here. Where is the equation 1? This is the equation 1. ds is equal to dou s by dou t at constant volume into T plus dou s by dou V into at constant volume, constant temperature into dV. Okay, so I'm writing once again that equation. What is our equation? First equation, that is ds is equal to dou s by dou t at constant volume into dt plus dou s by dou v at constant temperature into dv. Right now, what I'm going to do is I'm multiplying by t on all the sides, both the sides. So I will get T ds is equal to T into dou s by dou t at constant volume into dt plus T into dou s by dou v at constant temperature into dV. So you will get this relation, right? Now already we have two relations we have got before, that is dou s by dou v at constant temperature is equal to dou p by dou t at constant volume, right? This is one relation you got. And second relation is T into dou s by dou t at constant volume, T into dou s by dou t at constant volume is equal to Cv. So you got these two relations you got. So these two relations, this one and this one, these two relations I'm going to use here in this relation, in this equation. T ds is equal to T into dou s by dou t into dt plus T into dou s by dou v at constant temperature into dv. Okay, so these two relations I'm going to apply there. So when I substitute that one, I can rewrite this as T into ds is equal to T into dou s by dou t. Okay, substituting this, I can rewrite this as T into ds is equal to Cv into dt. You will get this relation, Cv into dt plus T into dou p by dou t at constant volume, dou p by dou t at constant volume into dv. So this is what you will get after substituting these two. That is, we are substituting T into dou s by dou t into v as Cv, and then dou s by dou v at constant temperature is dou p by dou t at constant volume. So I'm substituting that, and I got this relation, right? So once you get this relation, you can substitute this in the second law of thermodynamics. So from second law of thermodynamics, what is our equation? Du is equal to T ds minus P dv. This is our equation, right? So I can write du is equal to T ds. What is T ds? This is our T ds. T ds equation is this. We got this equation T ds, right? T ds. So I'm going to write that one equation here. So and minus P dv. Okay. So when I combine these two equations, T ds and P dv, when I combine, so I will write du. I can write this du as Cv into dt plus T into dou p by dou t, Cv into dt plus T into dou p by dou t at constant volume minus P whole into dV. This is what you will get. So du is equal to, right, du is equal to Cv into dt plus T into dou P by dou T at constant volume minus P into dV. This is your internal energy change. This is what you will get as internal energy change, du. You will get du, right? Now from van der Waals equation, from van der Waals equation, you already know van der Waals equation, P plus A by V square, P plus A by V square into V minus B is equal to RT, okay, for 1 mole of gas. So P plus A by V square into V minus B is equal to RT, okay. So now I can write this as a P plus A by V square, I can write as RT divided by V minus B, okay. So what will be your P? P will be equal to RT divided by V minus B minus A by V square, okay. And what is our equation du? Du is equal to Cv into dt plus T into dou P by dou T at constant volume, okay, dou P by dou T at constant volume minus P, okay, whole into dV. So this is your du, internal energy change, and pressure is here given to you. So what I am going to do is I am going to find what is dou P by dou T, dou P by dou T at constant volume. How much will be that? So that will come out to be R divided by V minus B, okay. If you differentiate dou P by dou T at constant volume, you will get R divided by V minus B, okay. This equation, if you substitute this equation, you simplify this du value. So when you simplify this du value, so du value comes out to be how much? Du value comes out to be, and here already we have seen dou P by dou T at constant volume is equal to RT divided by V minus RT divided by, right? So this relation you have got here. So this term, this whole term I am going to find out, that is T minus T into dou P divided by dou T at constant volume minus P, okay. That value will be equal to T into dou P by dou T at constant volume is R by V minus V. So RT by V minus B minus pressure. What is pressure? Pressure value you already know, that is RT by V minus B minus A by V square. So that means what? This whole term is what? This whole term is equal to A by V square, right? So our equation now will become this equation. Where is our equation? This equation du, okay. Our du equation will now become du is equal to Cv dt. Du will become Cv into dt plus this whole term is a T into, that term is A by V square. So plus A by V square into dV, right? So your du, that is the internal energy, comes out to be Cv into dt plus A by V square into dV. So this is the internal energy, right? So du is the internal energy change, and Cv into dt plus A by V square into dV. Here, what is dV? dV is nothing but V2 minus V1, okay. V2 minus V1. And what is V square? V square can be approximately written as V1 into V2, Okay, v square can be written as, for very infinitesimal small change, we can see that v square can be written as v1 into v2. Okay, v1 into v2. And for isothermal process, for isothermal process, your dt is equal to 0, right? Dt equal to 0. So this term becomes 0, this term becomes 0, and this term I rewrite it. So I will get du is equal to a into v2 minus v1, a into v2 minus v1 divided by v1 into v2, divided by v1 into v2. This is what you will get the internal energy change, right? So I got the internal energy change as a into v2 minus v1 divided by v1 into v2. Okay, now also we know that from the first law of thermodynamics, in that we have the work done value. What is work done? Work done is equal to P into dV. Okay, and what is P? P already you know from the Van der Waals equation. It is RT divided by V minus B minus A divided by V square. Okay, so what is work done? Total work done. Total work done is integral dW. Okay, you are integrating dW, which is equal to integral P dV. So P is here, pressure is here, you are integrating it from the volume V1 to V2. Okay, so when you integrate this and you solve it, you will get the work done value. How much you will get? RT divided by, RT into ln of V2 minus B divided by V1 minus B. This is what you will get, R2, plus second term you are getting A into V2 minus V1 minus V2 by V1 V2. Okay, so these two terms you are getting, but you can see that this term, the first term, is much larger than the second term. Okay, so this term, this particular term, okay, this particular term is very small, so you can neglect it, you can take it as 0. All right, so what will be your work done? Your work done will be equal to, finally the work done will be equal to RT into natural logarithm of V2 minus B divided by V1 minus B. Okay, RT into natural logarithm of, this is the work done. Okay, and already we have seen the internal energy. What is the internal energy? A into V2 minus V1 divided by V1 V2. So internal energy change is equal to A into V2 minus V1 divided by V1 V2. So we have the internal energy change and we have the work done, right? So what is Q? Q is equal to internal energy change plus the work done. So if you substitute this value here, so the internal energy change and work done, if you do, so you will get the Q value. Q value is equal to internal energy, I am writing as A into V2 minus V1 divided by V1 V2 plus the work done, that is RT natural logarithm of V2 minus B divided by V1 minus B. Okay, so now here since for oxygen, for the B value for oxygen, B is equal to approximately 0.032. The value of B is approximately 0.032 units. Okay, for oxygen. So this is very small value. So you can approximately write this Q. I can write this as I will take this first term. I will take one V2 outside. V2 I will take outside. So I can write this as V2 divided by V1. Okay, minus 1 plus Second term I can write as RT ln of natural logarithm of V2 divided by V1, and I'm going to take V2 divided by V1, I'm going to take as X. V2 divided by V1 I'm going to take as X. So I will get a Q is equal to A by V2 X minus 1, A by V2 X minus 1 plus RT natural logarithm of X. Okay, so this is the formula for finding the finding the uh, value of V2 divided by V1. Okay, so in this case you can see here that this X is the value V2 divided by V1 is X. So in this value, if you want to find X, then V2 is very important, right? So we need to find V2 here. We need V2 here for finding the solving the equation. So in this way we can find out the value of V2 by V1 by how much value the volume has changed. So we got the value of the change in the volume, we got it here, but for that this term V2 is very important here. Okay, so final V2, that is a final volume. V2, that is final volume, is required here, right? So the final volume, how much is the final volume? That final volume is required here to find the value of X. Okay, so this is how we find out the change in volume in the case of a real gas. Okay, not an ideal gas, it's a real gas.